So let's go ahead and take a problem and see if we can apply this problem-solving strategy to it. Now, as an example of using this problem-solving strategy, I'm going to take a question from one of the chapters in your book, and this question is, how long does it take for a ball to fall 2 meters, and how fast is it going when it reaches the floor? So the first thing I'm going to do for my strategy is I'm going to rewrite the question. Okay, so I've just restating the problem here. Now that I've restated the problem, I'm going to identify the model we're going to use. So the model that I'm using is we have a ball falling due to gravity. And because we know the model, we already know some of the parameters we're going to need. So let's go ahead and visualize this. And I understand that you can visualize a ball falling, but again, part of what you're doing here is just training your brain to slow down and think about the problem. So that's why it's kind of nice to draw a little box there. We've got this ball. It's going to be falling down. It's experiencing a force due to gravity. It's falling 2 meters distance, right? And we want to know how long, the time. We'll call that t. We want to know the velocity. We'll call that v. Okay. So my knowns. I know the acceleration due to gravity. That's 9.8 meters per second squared. And my unknowns, we have the time it takes to fall, we'll call that t, and we have our velocity, call that meters per second, call that v. Let me erase that there. Call that v, meters per second. Okay. So my strategy is laid out. I have a good idea of what I'm trying to do. I need something that relates gravity to those knowns and unknowns. Oh, I have one other known here, right? The height that it's falling from. Let's call that y. Call that 2 meters. Okay. And you'll notice I've listed the values along with their units there. Okay. So now I need to do a solution. And maybe even before I do the solution, though, I might want to ask myself, well, what do I expect the answer to be? Well, this is one of those things that you can kind of do an experiment, right? Pick something up about 2 meters off the ground and drop it. And you're going to find that if you do that, that it's taking of order about a second, right? So we already know, I mean, we can kind of come down here to the significance part. And we can already kind of, put our assessment in here and say we expect the time to be something like 1 second, right? So we expect it to be something like 1 second, at least of order. That's our expectation. By the way, that right there gets you pretty far towards the correct answer, because that's actually the correct answer, or pretty close to it, and you've identified the knowns and unknowns, you've identified the problem. Okay, so let's go ahead and do the solution for this. The solution for this requires that we know how these things are related to each other. And I can kind of already see that if I think about the velocity first, right, I can look at the units of velocity. The units of velocity is meters per second, right? And my units of acceleration is meters per second squared. So I'm going to guess that my velocity is going to be the product, if I think about my time over here, my time is in seconds, the product of acceleration and time should give me velocity. So I'm guessing here that the velocity is going to be gt, right? And the units work out for that. And if you think about for something falling at a constant acceleration, I expect the velocity to be increasing linearly as I fall. So if I think about a graph of this, this is a graph of velocity versus time. I expect it to go up like that. And the slope of that line, the slope is g. So from unit analysis, I can kind of figure out what that should be, although you can go look up in your book and find out that velocity is related to acceleration that way, assuming I'm starting from rest. So I already had part 2 of this, what the velocity is. So now I'm going to go ahead and put those values in. The velocity is going to be equal to 9.8 meters per second squared times my time. Now you'll notice I don't know what the time is, right? Because that's the first part. So let's go ahead and figure out how we can solve for the time. So I don't quite have the full solution here because I don't know what the time is, but I at least know that if I put in the time in seconds, that's going to give me the velocity. So the second part is to look at the position as a function of time. Now, because the velocity is constantly increasing, the position is not going to be linear. It actually is going to start at 2 meters, and it's going to fall. It's not going to fall with a line, right? Because that would mean that the velocity was constant. The velocity is constantly increasing, so it's going to fall faster and faster and faster over time. So it's going to make this curve like that, which means that it's going to, in the same amount of time later on, it's going to drop a further distance than it does initially. So what is the equation that we have there? Units would tell us acceleration and multiply it by distance or by time squared. That should unit-wise give me position. And it turns out that there's a 1/2 in there because this is a constantly increasing velocity. And you'll see in class, we'll talk about where that comes from. But the relationship between position, acceleration, and time is given by this equation, and we have a 1/2 in there because the velocity is constantly increasing with time. But if I look at the units of this, I've got meters per second, I've got time, meters per second squared, I've got time squared, so the units are in meters, so that works out. So let's go ahead and solve this for time. My time is going to be equal to 2 times y divided by g square root. Okay. And I asked what that was, so we can go ahead and put that in. So that's 2 times 2 divided by 9.8. And just to put the units in here, this is meters per second squared. I have a square root, so this is going to give me units of seconds in the end. If I take that out of the square root, units of seconds. And that gives me the square root of 4 divided by 9.8. And that turns out to be 0.64 seconds, which is of order 1. Okay, so that makes sense. And now I can go ahead and plug that in for my velocity here. My velocity, just coming back up to this, is just 9.8 meters per second squared times 0.64. And if I do that, that's going to be roughly 0.64 times 10. So that's 6 meters per second of order. Okay, so down here in my significance, I say that my time is about 0.64 seconds. My velocity is about 6 meters per second. And the units work out. Units are good. And the values make sense. Now, if I wanted to take this further, I could go ahead and work out, meters per second might not be the best unit for you to think about. So if I take 6 meters per second times, let's say kilometers per hour is a reasonable one. I'll say there's 1 kilometer is 1,000 meters. And then I'll say that 3,600 seconds is an hour, right? So my meters cancel out, my seconds cancel out. my 2 zeros cancel out. In fact, one more zero cancels out, and I get 6 times 3.6, which is like 20, right? So that's something like 20 kilometers per hour. And that is something that I can say, okay, yeah, that totally makes sense. So that gives you an idea of how to write these solutions out. I want to point out something that you'll notice I used at least one page, an entire page here for that. And that's what I expect. I expect the problem to take at least one page, and some of the more complicated problems will take even more pages than one. So your homework assignment should have a separate sheet for every, at least one separate sheet for every single problem. And that's so that you have space to do all 3 of these. Okay, so we'll go ahead and stop with that. I just wanted to give you an idea for problem solving. You'll see this, I'll do more examples of these as we go, as we do more problems. But I hope that gives you an idea of how you can solve problems in physics.